All right, today we're going to talk about something called CMOS RF integrated circuits. Now, I know that sounds like a mouthful, but really it's just the fancy name for the magic that makes your phone, your Wi-Fi, and your Bluetooth all work. And there's a much simpler way to think about what we're really getting into here.
See? At the end of the day, we're really just talking about circuits for cell phones. It's all about those tiny mass-produced radios that have completely taken over our wireless world. We're talking everything from Wi-Fi and Bluetooth to the GPS that keeps you from getting lost.
Now, every single one of those radios has two fundamental jobs. First, it has to transmit a signal out, we'll call that TX. And second, it has to receive a signal in, which you guessed it, we'll call RX. To really get how this works, we need to meet the two star players on either end of this whole process. Okay, so on the receiving team, you've got the low noise amplifier, or LNA. Its whole job is to take a super faint signal coming in from the antenna and boost it, but, and this is the key part, without adding a bunch of its own static. Think of it like a super sensitive microphone. Then on the transmit team, you have the power amplifier, or PA. It does the complete opposite. It takes your signal and basically blasts it out with as much power as it can so that the cell tower can hear you loud and clear.
So let's just follow a signal on its journey into your phone. It starts as this tiny electromagnetic wave flying through the air, and it gets picked up by the antenna. The very first place it goes is to our LNA, which gives it that all-important initial boost. From there, a component called a mixer shifts it down to a more manageable frequency, and then finally, the processor can turn it back into the voice or data it was always meant to be.
That path sounds pretty straightforward, right? But here's the catch. In the super high-frequency world of radio waves, there's a huge challenge that pops up at every single one of those connection points, something called signal reflection.
And that leads to the million-dollar question in RF design. If the energy can't flow perfectly and smoothly from one component to the next, where does it go? I mean, it can't just vanish into thin air.
Well, it bounces back. And this whole problem is called an impedance mismatch. The best way to think about it is like hitting a solid wall in the middle of an electrical highway. When the signal hits this break between two components, a good chunk of its energy just reflects and goes backward, which, as you can imagine, creates total chaos in the circuit.
And this quote just nails why this is such a big deal for, say, a phone call. If you have a bad impedance mismatch, that really powerful signal you're trying to send out can actually leak and bounce right back into your super sensitive receiver. And what's the result? Instead of hearing your friend, you just hear an echo of your own voice completely drowning them out.
So how do we fix this mess? Thankfully, engineers have a really elegant solution. It's a core principle called impedance matching, and it's basically the art of creating perfectly seamless connections so none of that signal ever bounces back. And in the world of RF, the magic number is 50 ohms. Why 50? Well, after decades of research, it turns out that 50 ohms is the perfect compromise, the sweet spot, between handling maximum power, which is best around 30 ohms, and minimizing signal loss, which is best around 77 ohms. So 50 became the universal standard. The whole goal of impedance matching is just to make sure that every single component in that signal chain, the antenna, the LNA, the PA, all of them, is designed to look like it has a 50 ohm impedance right at its connection point. When you do that, the electrical path becomes perfectly smooth. So let's break it down. When the load impedance, say from your LNA, doesn't equal the source impedance of the antenna, you get reflections, echoes, and lost power. But when they are equal, all the power gets transferred, you get zero echoes, and everything just works. And this means more than just clearer calls. It means better signal and even better battery life for your phone. So in the real world, this means the LNA's input has to be perfectly matched to that 50 ohm antenna. And on the other side, the PA's output also has to be matched to that very same antenna. In fact, every single connection along the way has to be perfectly matched to keep that signal path clean. Okay, so you get the problem and you get the solution. But what if you're the one who actually has to design these circuits? What are the fundamental tools you really need to have in your engineering toolkit? You know, it really just boils down to these three things. First, you need a rock-solid understanding of basic passive circuits, your resistors, inductors, and capacitors. Then, you have to learn to think about wires not just as simple connections, but as complex transmission lines. And of course, you absolutely need to master the MOSFET, the tiny little transistor that is the building block of pretty much all modern electronics. It's kind of crazy when you think about it. We just saw how a simple electrical property like impedance can make or break how well your cell phone works. Understanding these deep, fundamental principles isn't just about passing a class.
It's the key to designing the next wave of wireless tech. It really makes you wonder, what other invisible forces are shaping all the technology we rely on every single day?